Hello, people. Continuing on mad dash to catch up from some of the classes that we missed, I wanted to wrap up our discussion of explicit heap dynamic variables. I've got a quick summary of the example that we looked at in C, where what we're doing here is we're allocating a node. We're using a special, I forgot to do the node star here, I just noticed that. Okay, we're using a special form, a special memory allocation mechanism called malloc, and what malloc is going to do is allocate a certain number of bytes, and specifically node size number of bytes, and set n, link n to that chunk of memory that's of size node, and then we can start treating that chunk of memory as a node. Now, one of the things you have to do when you're dealing with the language of C is that you have to be explicit about getting rid of the node when you're done using it. So you notice there's a method called free. So I have to say free n, and that means I'm done using the node. If I don't say free n, then the node that's pointed to or referenced by n will hang around forever, and that's not such a good thing. All right. Now, in C++, we could do something like this. We could say node star n equals new node. And likewise, what we're going to have to do is make sure that when we're done working with the node and we don't need it anymore, we're going to have to free it. And the way you do that in C++ is you say delete n. So again, this must be explicit. And if we take a look at this in Java, it's great. In Java, I say node n equals new node. And when I'm done with node n, what's going to happen is it's going to get cleaned up implicitly. So I don't actually have to do anything to get, I'll say implicit cleanup. I don't have to do anything explicit to get rid of node n. When I'm done using it, what will happen is, well, if you want to get really technical about it, if this is, let's say this is a code block, all right? So I just made a block of code. This might be a code block because I've entered some method, or it might be a code block because I entered an if statement. But when I enter this code block, this node n, the space for the reference, right? The reference to the node, not the actual node. This is creating the node here, but the reference to the node here, the space for that gets created on the stack. And then I create new node, and I now have n, which is on the stack, referencing the node, which is on the heap. Now, when I exit this code block, in other words, whether I exit a method or I'm exiting an if block or a for statement, a block of code for a for or a while loop, when I exit the block, this n goes away. It's removed from the stack. The node doesn't go away, though, because the node was created on the heap. So what's going to happen is the garbage collector, I can't rate it here, I don't have enough space, but the garbage collector in Java is going to come along and look around, and it's going to look for chunks of memory that are on the heap that don't have references to it. In other words, chunks of memory that are on the heap that have been allocated that don't have any references that are interested in it. And this node will be one of those, and so the garbage collector will destroy the node. All right. Well, there's one other thing that I want to talk about in terms of address binding, and that is a mouthful: implicit heap dynamic variables. So implicit heap dynamic variables are variables where memory is carved from the heap. But it's not via an explicit method call. So there are languages that do this. For example, if I were to use JavaScript, I might have something like this. List equals 10, comma, 3, comma, 2, semicolon, list equals 3, semicolon, and then list equals hello. So in each case, the variable list is a variable that is continuously being rebound to 3 separate chunks of memory. This one, and this one. The first chunk is an actual list. The second chunk is a numeric. And the third chunk is a string. Now, there's no way to do this rebinding. It makes no sense to do this rebinding as an implicit stack dynamic rebinding, because we really have no idea at the moment we enter a method how big the stack is actually going to get. So what we do instead is we bind the list variable to chunks of memory in the heap. So first we're going to bind it to a 3-element list, and then when we're done with that, when the next assignment statement, we unbind list from that 3-element. We unbind the list variable from the 3-element list, and we rebind it to the numeric 3. Then we unbind it from the numeric 3, and we rebind list to the string hello. So the advantage of this type of binding and unbinding, frequent binding and unbinding, is pretty much the same advantage as the dynamic type binding. You get a really nice ability to do generic programming. And what I mean by that is, the example I gave before, I'll just sort of reiterate it. The idea is, if you wrote a sorting routine, and the list of stuff that you're sorting in the sorting routine, whatever type stuff is, really doesn't matter if you've done a good job of writing the sorting routine. And so you can take advantage of reusing that same sorting routine over and over again, the same code for lots of different types, whether you're sorting a list of numerics or a list of strings or a list of dogs or whatever. It doesn't matter, as long as you can get that comparison operator to make sense for the types that you're working with in the list. The disadvantage is that there's performance cost. So that's the happy part. Here's the sad part. Okay, the performance cost here, with type binding, the performance cost was we had to do continual type checking. Every time we did any kind of operation, we had to make sure, well, for the type that this variable is right now, is this a valid operation? But when you're dealing with thinking about address binding and unbinding, the issue here is that there's a lot of junk as you unbind a variable from one memory location and then rebind it to another memory location in the heap. There's a lot of junk that gets put into the heap, and someone's going to have to clean up that junk and manage that junk. And so typically you have some kind of garbage collection scheme, again, kind of like what you have in Java, to handle that. Okay. Well, that takes care of our discussion of a wrap-up of address binding. So the next thing that I'm going to talk about, which will be in a separate video, is the idea of scoping, which isn't just a mouthwash. So we'll talk about that next.